first in each of these orbitals before I start pairing and having the negative spin that will correspond with those positive 1/2 spins, okay? So ultimately this table, what is it, 6.3 in your book, just shows the orbital diagrams from lithium to sodium. So I'll see that if S can only have one shape, I should only have one box. P has 3 different shapes, so when I draw the orbital diagram, I should have 3 different boxes. S, again, has one shape, I should have one box. If I were drawing the D orbital, I would want that D orbital to have 5 boxes because there are 5 shapes. Okay, if we were to kind of fill in our periodic table technically the way that it would be really long, elongated like this. So I have my S, I have my F orbitals here, I have my D orbitals right here, and then the P would be right here, okay? If we want to write the shorthand configuration for the electron configurations, we call that the noble gas configuration. So I'm going to write whatever noble gas is, ultimately I'm going to find whatever element, whatever energy level that element is at, whatever row on the periodic table it is, and then I'm going to go to the noble gas right before I started that row. So there's 2 parts that are considered in a noble gas configuration. There's the portion that's called the core electrons, and then there's the portion that are the valence electrons. So the valence electrons are those outer electrons that are able to partake in bonding, and then those core electrons are going to be one that have a greater Coulombic attraction to the nucleus, so they're going to be much more difficult to get away from the nucleus, okay? Now, you saw some examples of that on the homework or on the paper that we got for Friday. So if we want more of this, let me know and we can do more of that. We'll probably do more of that on Monday anyway, just to make sure that we're good. Okay, we also alluded today in class to a couple of exceptions to our electron configuration rule. So there's 2 exceptions, and those are in the d orbital. So the copper column in the d orbital, as well as the chromium column in the d orbital. And this should totally say the electron configuration for chromium. This should definitely not be for copper. So guys, can you change that for me in your notes? This should say the electron configuration for chromium is 4s1 3d5 rather than 4s2 3d4. So why does that happen? It happens because the d orbital, since it has an energy level of 3, it would prefer to be full first. I want to make sure that I'm filling up energy levels of a lower principal quantum number first before I'm filling up one of a higher energy level, okay? So that's why, even though we expect 4s2 3d4, the D is going to take 1 from the S, because now at least I have 1 electron, with a positive half spin in each of the orbitals, so it just makes things, it brings a lot more stability versus this one, and really it's all about stability. So copper or chromium column will do this, and then the copper column will do that, okay? Last thing that let's allude to is something called a photoelectron spectroscopy. This is kind of similar to the radial distribution that we talked about before, only I think this is so much easier to read. So for photoelectron spectroscopy, it's a technique that we use to measure the energy and then also the number of electrons in an atom, okay? So when I mean number of electrons in the atom, we're also going to say that that's equal to intensity. So intensity is going to be graphed on your y, and then the amount of energy that we see is going to be here on the x-axis. So how does this work? We take a sample of a certain element, of any type of isotope, and we bombard that sample with X-rays. Or we've also been able to do this with UV light, but X-rays work a lot better. So I bombard this sample, and specifically this is for neon. So I take neon, I bombard that with X-rays. what happens is the X-rays collide with the electrons that are in neon or in whatever sample that we have. And it makes the electrons become so excited that then they end up becoming ejected from that sample. So it's very similar to the photoelectric effect in that I bombard a clean piece of metal with some type of radiant energy. The electrons absorb that energy and the metal ejects the electron. So very same process. Then those ejected electrons are going to ultimately interact with a detector, which is going to measure the amount of energy that those electrons have. So let's kind of read this graph. So if we think about the electron configuration for neon, we know that that's 1s2, 2s2, 2p6, okay? If I'm looking here, each peak is going to represent one of those particular orbitals. So we had 1s2, 2s2, 2p6. If I'm graphing energy versus intensity, which one of these has to be the 2p6 orbital? It has to be this one. It has to be the tallest one because I have 6 electrons in this really tall peak versus the other ones which are smaller, which then would mean that I would have about 2 in those peaks. So this is my 2p6 peak. This then must be my 2s peak, and this is my 1s peak. But why do I read it in this direction? Let's look at the amount of energy that these electrons have. The energy here is 870, and that's EV stands for electron volts. So this would be 1s. For 2s, it's 48.47, and then for the 2p, it's 21.61. Will it take a lot of energy to get the electrons in the 2p orbital to be ejected from neon versus the amount of energy it's going to take to get the 1s electrons away from the nucleus? It's going to take a lot more energy to get off the 1s electrons, right? So these are going to show, whenever they interact with the detector, a lot more energy because I'm going to need to give them a lot more excitement before that atom will eject those electrons. There's a lot more Coulombic attraction happening between these electrons with the nucleus than there are these electrons and the nucleus, okay? So that's how we're going to read a photoelectron spectrum. So we're going to do a lot of practice with these in terms of AP style or AP level questions on Monday. We're also going to do some more electron configuration and quantum number practice on Monday. And then after we do that, we're pretty much done with chapter 6. And then we're going to move straight on into chapter 7. So again, on Tuesday, I know that's redo day. So if you would write for me or make a comment on the blog to say, yes, you're going to redo day, or no, you're not going to redo day, that would help me so much. So please make sure that you do that. Okay. We will, I will also post that key on your blog on Sunday night for the paper that you got on Friday. I hope you guys have a really wonderful weekend. See you at the game. Bye.